Hello guys, welcome back to my channels. So today I'm going to talk about electron spin resonance. So in this video I'm going to cover the spectra, how we'll get the spectra through the transitions and lines, how we'll see the lines, okay, uh, in the presence of uh, different protons, how we'll get lines, mm, all those things I will discuss in this video. Okay, so let's start. So electron spin resonance, that is EPR spectra. So here basically if the molecules uh, have presence free radicals or ions, okay, so these types of molecules will give the ESR spectra. Okay, so the phenomena of now discuss the phenomena of electron spin resonance called the electron paramagnetic resonance. Okay, so the here the both NMR and ESR are collectively referred to as a magnetic resonance phenomena. So NMR and ESR both are done under the magnetic resonance phenomena. Okay, so this ESR spectrum ECR technique has limited application because it observed primarily in the systems that containing unpaired electron. Okay, so initially uh, 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 peoples have observed limited application, because those compounds who has only unpaired electrons that present that only the applicable for the ESR measurements. So, but now the organic, inorganic, free radicals and ion, those molecules have present ions also gives the transitions. Okay, ions of transitions metals. Okay, and unpaired electron I already discussed of D or F electrons that investigate through this techniques. So most important points is here. So the the detection extremely short-lived free radical intermediate in chemical reaction. Through this, we can investigate the short-lived free radical intermediate. Okay, so these are the some highlighted important points in this electron spin resonance. Okay, so now we talk about the spectra. How you will get the spectra? Okay, so ESR spectra of unpaired electrons. The if the systems have presence single electrons that show the spin value plus half, and how it work when apply the magnetic fields this uh, uh, electrons. Okay, so this is the y-axis energy levels, and this is degenerate levels in absence of magnetic fields, so it will not give any splitting. Okay, but when we apply the magnetic fields, it will give some lines like splitting lines, sorry, splitting energy levels. So here this, after applying the magnetic field, you will see the two energy levels. So these the difference of these energy levels plus half and minus half will see GE may be B. where mu b is the Bohr magneton and G is the Lande factor and B is the magnetic fields. Okay, so here the transition will not taking place because delta I delta mi value is not 0, because if you uh, but ms value is plus minus half. Okay, so that's why you will not see here any transition. Okay, but you will get through this, you will get a spectra, that is absorption spectra. Okay, so now we'll discuss the hyperline, that is most important hyperlines structure in this ESR spectra. How we'll see the hyperpine lines. Okay, after this ESR spectra. So that's things I will discuss. Okay, in the next um, slides. So before we start, we have to know the some important points. So important point is that the here the interaction, magnetic interaction between the electron spin and nuclear spin will happen. Okay, without this will not uh, give hyperfine lines or structure. So and another thing is that at the selection for that hyperfine transition, you will need the selection rules. That selection rule is delta ms should be plus minus 1 and delta mi should be plus minus, sorry, 0. So this is the selection rule for this hyperfine structures. So now take one example for hydrogen atom. This hydrogen atom contains single electrons. Okay, single electrons, and that shows the s value is half and I value is half, and ms value is plus minus 1 and mi value is plus minus half. And this hydrogen atom shows single proton. So this single proton, you will see the lines and plus 1 lines. Okay, because one proton give 2 lines due to the n plus 1 rule. Okay, earlier if you remember, earlier I discussed due to in NMR spectrum. So how this like neighboring group will affect through the each other through n plus 1 rule. Okay, so similarly for this single protons atoms, the ms value is plus minus half, give degenerate lines in the absence of magnetic fields. And when you apply the magnetic fields, it is split into two levels, plus half and minus half. But the here hyperfines is, spectra, you will not get hyperfine spectra. Okay, because the transition will not taking place. But this from here you will see the hyperfine spectra. Okay, so this ms is again split to the two levels. Okay, due to the presence of magnetic fields, but you will not but here you will not see zero values of hf because the transition is taking place. Okay, so these four energy levels, due to the this mi, you will see the two transition. One is from minus half to minus half, another is plus half to plus half. So this transition is taking place due to when you apply this delta mi is equal to 0. This if you this hold, then the transition will taking place. Okay, so here you will get two lines. So due to this you will see the experimental spectrum. So here you will see the two peaks. One peaks through this transition, another peak through this second transition when you apply the magnetic fields. Now take second example. So second induction examples, methyl radicals. Okay, so here S value is half and I value is half for protons, but here the present three protons. Those three equivalent protons, that means n plus 1, that is 4 line. You will get the 4 equally spaced lines, that is quartet, and mi value you will here see 3 by 2 plus half minus half 3 by minus 3 by 2. And similarly, initially this will show degenerate level in absence of magnetic field, and presence of magnetic field you will see the two levels, split energy, two levels. Okay, and again this is split into four levels due to the mi values, and similarly this also. So here you will see four transition, and due to four transition you will get four lines. Okay, this you will see four spectra. Okay, and this ratio shows the Pascal's values, 1 is to 3 is to 3 is to 1. Okay, but here the B and magnetic field and HF value will not zero, because transition you will get, and due to the applying magnetic field you will see the this transition. Now we talk about third example. So these examples have some importance. So these examples SO3 and O2, SO3 का whole twice, NO minus anion. This contains single electrons that interact with nitrogen nucleus that spin source 1, sorry, I value for nuclear spin source 1, and MS value source plus minus half, and this Mi value you will get uh, plus 1, 0, minus 1. This spectra contains three equally spaced line, that is triplet. So as I discussed in NMR, the for even mass numbers of nitrogen you will get plus 1 value, sorry, 1 value for nuclear spin, and for odd mass numbers you will get I value is half. So but here the mass number is even, that's I here I consider I value is 1. So similarly in first stage you will get degenerate level, and after applying you will see the this splitting. Okay, after, and then again you will see the hyperfine spectra due to the presence of magnetic fields. Okay, so you will get three lines here, and experimental spectra you will see three peaks. Okay, so this for example, so for example one for benzo semiquinone radicals. Okay, here present four protons, so single electrons was as value is half, and that interacting four equivalent protons. For protons I value is half, and 4 proton gives the n plus 1 line, that is 5 lines. So 4 equivalent protons and mi value will be plus 2 plus 1 0 minus 1 and minus 2. This I value actually represent the this degenerate sorry, this split energy levels. This is split energy level, and because this give 5 transition. Okay, so this first ms value will give 5 transition, and this minus half value give 5 transition. 5 energy level, so you will get the 5 transition, and 5 transition give 5 lines. So you will see this experimental spectra 5 peaks, and Pascal ratio 1 is to 4 is to 6 is to 4 is to 1. And these last example, 3 example is very important examples. Here is not present any radicals. Okay, here present anion, minus sign. So okay, but earlier example, uh, uh, we have get lines through radicals, but here we will get lines through anions and that present protons. Okay, so these naphthalenes negative ions here present. This is the like molecular structures. So here you will get two types of protons. So this alpha, beta, beta, beta. So here two sets of protons. You will get two sets of protons, that is alpha and beta, and each sets you will see four protons. One, two, three, four. Alpha is 4 and beta is 4. So therefore line you will get 4 plus 1 due to this alpha, and 4 plus 1 into 4 plus 1 due to beta. So if you multiply these things, you will get 25 planes. Similarly for anthracene, so here you will get 3 sets of protons, alpha, beta, gamma, and similarly you will get lines, 75 lines. Similarly for this triphenyl methyl radicals, you will get 3 types of protons, and lines you will get 196 lines. Okay, so at the end we will see notes points, some notes points, summaries points. So is ESR a spectrum of a system where unpaired electron interact with unequivalent protons that contains lines n plus 1 lines, and their relative intensity are given by Pascal triangle. Okay, so as I discussed these examples, so H atom give two lines, that is doublet, that is equally intensity, and this methyl radicals give four lines, quartet, that intensity is this. And last two points is very important, and those nuclei that I value is greater than half, that apply other rules. Okay, here the protein and that is even mass number. For this case, the I value is 1 and give hyperpine line, that 3 equally intensity. And last one, this copper 63, that is odd numbers, that I value you will see 3 by 2, and intent that interacting with an odd electron gives hyperpine line 4 of equally intensity. So this is all about ESR. Okay, electron spin resonance. So hopefully you understand these lectures. So if you found this video interesting, okay, so don't forget to comments and like and subscribe. So thank you for watching.